Okay, guys, let's start today. As some of the more students are in class today, last lecture there were not too many, so we had a lot of mathematics last week as well. This was the preview that I am showing you from last 3 weeks. In the first 2 weeks, we concluded history part of crypto. Then we go through the symmetric crypto. Now, today, the third week and the last week of cryptology, we will learn about hash functions and obviously the asymmetric crypto, which is remaining. Yeah, then there will be the end of crypto lectures. Starting with hash functions, it is actually a function that takes input. That input can be of any length, arbitrary input, and it gives us a fixed size output. This hash function is called as a deterministic function. That means it will always have output on a given input. Yeah. So here's the definition. A hash function is a deterministic function that takes a binary input of arbitrary length and maps it to the binary output of fixed length. That means the input can be of any length. We have the fixed length of output. Goal of this hash function is to produce obviously the output which will be of fixed length. There are some of examples of these hash functions which we will learn today. Some have 128 bit of values. Some are 160, that SHA-1. Then SHA-2 and 3 came up with enhanced versions as SHA-1. There are some properties, some pre-requirements of hash function. First one is which is called one-wayness. For example, if you have a output of a function, say you have a y, it is difficult to find the input that maps to that output. This is one-wayness, and it should be a hash function should hold this. Yeah. That means it should be difficult to get the input that maps to that output if you only know the output. Second thing is what we call as weak collision resistance. This time I'm not showing you the output. I'm telling you that I have an input, say x0, and if you come up with a say another input, say x1, that maps to the same function, say y. Yeah, that's called weak collision resistance. This means that the first one, that the property means that it should be computationally hard to reverse the hash function. If you already know this is about the first one. And in second thing, if I have an input that maps to the function, there should be hard to get one more input, say x1, that maps to the same to that function. Third one is strong collision resistance. This is somewhat related to the previous one, where we have say a hash function. You come up with two inputs, x0 and x1, or x1 and x2, that maps to the same hash function. Okay? This should be also very difficult. These are actually the requirements for the hash function. There are some properties of hash function that it possesses the avalanche effect. Avalanche effect is simply if you have an input and you have corresponding output, although the output will be a fixed length with respective of the input length. And the avalanche effect is if we change a bit in the input, it should lead to change the half of the bits on the output. That's called the avalanche effect. Why so? So as if anyone comes to change the input somehow, there should be completely different output. At least 50% of the bits should be changed. Yeah. One more property, that it should be very easy to compute using our hardware and software. Although if we have say infinity number of inputs and we have some fixed outputs, there can be possibility that there is collision, that you come up with one more input that maps to the same output. The goal is that it should be impossible to, it should be like very hard, not impossible, it should be very hard to find that input. Some of the techniques, hash function techniques who are working, then these hackers, cryptanalysts came up with the collision function. So they are not being used anymore. That's why we moved to new techniques. Yeah. We have different constructors to construct hash functions. One is we use block ciphers for the construction of hash functions. Second is we use MD families. These are actually hash functions, which includes MD5, SHA-1, SHA-2. Yeah. And more about these MD families, that MD5, it has an output of 128 bits. This is the specification of these MD5 and SHA-1 and SHA-2. Yeah. It comes up with 12 bits of block size with 64 rounds. We will see what those rounds are. Then collision has been found there on MD5, so it is not secure anymore. So move to SHA-1, where also we found the crypto analysts have found the what we call as collision, and now it's not being also used for so many techniques. SHA-2, which is the enhanced version of SHA-1, which used say output bit of 224, 256, 384, 5112 of bits. And there are rounds, those rounds we will discuss in a few slides, but yet the collision has not been found. So it's being used. This is the Markle-Damgard construction, MD, that I told you in the first slide, the previous slide. If you see that you have seen this figure as before as well. There are blocks. Yeah, the message is divided into blocks. Then what we do is we have an initial value that we somehow calculate with the function, and output of that function is given to the as an input to the next function, which actually is the message block 2 out of all the message, and we keep on doing this till the end. And at the last, we get what we call as hash. This is one of the techniques to calculate, to compute hash. Yeah. And if you see the message has been divided into blocks, last you see that is written padding. For example, if we divide the message, say 512 bits, and in the last block, if we have message, some of the characters of message and remaining is empty, we used to pad that empty spaces with some say bits. We will tell you what bits we will use for padding in a few slides. This is there's a block size, and here if we see initial value, the output size of function first will be the same as the output of this initial value, so that their outputs will be same, and we will get at the end a hash function with some say fixed length.